Right now, as you watch this, something is moving through our solar system that shouldn't exist. Not according to our models. Not according to everything we know about how comets behave. It's called 3I Atlas, and it's the third confirmed visitor from interstellar space. But here's what makes it different from anything we've encountered before. It's breaking rules we didn't even know could be broken. Let me show you what I mean. This object is currently spewing water vapor at a distance where water shouldn't exist in gaseous form. It's traveling on a trajectory that seems almost too convenient, too perfect for gravitational assists. And its chemical signature? Well, that's where things get really interesting. Because what we're seeing doesn't match any natural comet we've ever studied. Now, I'm not saying it's artificial, but I am saying that scientists at Harvard, at Keck Observatory, at NASA, are asking questions they've never had to ask before. Questions that make some people very uncomfortable. The data from the Keck telescope shows something unprecedented: intense nickel emission without iron. In nature, these elements appear together. Always. Except in one scenario. Industrial nickel refining through a process called the carbonyl pathway. A process we invented. A process that requires specific chemical engineering. But we're getting ahead of ourselves. Let's start with why this object has captured the attention of every major observatory on Earth, why spacecraft are being redirected to study it, and why some researchers are staying very quiet about what they're finding. 3I Atlas entered our solar system from the direction of the galactic center, a region so crowded with bright stars that detecting a small moving object there is nearly impossible, almost as if it knew the best route to avoid early detection. When it was finally spotted on July 1st, it was already inside Jupiter's orbit, moving at over 210,000 kilometers per hour. That speed tells us something crucial. This isn't some rock that wandered out of the Oort cloud. The trajectory is hyperbolic, which means it came from interstellar space, from another star system entirely. Only 3 objects in human history have been confirmed with this distinction. The first was Oumuamua in 2017. The second was Comet Borisov in 2019. And now, 3I Atlas. But unlike its predecessors, this one is doing something that has scientists recalculating everything they thought they knew about cometary physics. In October, the Swift telescope detected water vapor pouring from this object at a rate of 40 kilograms per second. 40 kilograms. Every single second. To put that in perspective, that's like emptying a bathtub into space twice every minute, for weeks on end. Here's the problem. 3I Atlas was 3 astronomical units from the Sun when this was observed. 3 times the distance between Earth and the Sun. At that range, comets are supposed to be frozen solid. Water ice needs heat to sublimate, to turn directly from solid to gas. And at 3 AU, there simply isn't enough solar radiation to power this kind of activity. Normal comets don't wake up until they're much closer, usually inside Mars's orbit. We have decades of observations confirming this. It's basic physics. Solar heating decreases with the square of distance. At 3 AU, the sun's energy is 9 times weaker than it is at Earth. So how is 3I Atlas generating this water vapor? That's the first mystery. And it's one that doesn't have a comfortable answer. Some scientists suggested internal heat, radioactive decay perhaps, or residual warmth from its home system. But the math doesn't work. The amount of energy needed to sublimate 40 kilograms of water per second would require a massive internal heat source. And if that existed, we'd see other signs. Infrared signatures, unusual outgassing patterns, surface changes. We see none of that. The water just appears, defying the thermal models. Then there's the composition issue. When the James Webb Space Telescope turned its infrared eye toward 3I Atlas in August, it found something unusual. The dominant molecules weren't water, as you'd expect from a typical comet. They were carbon dioxide and carbon monoxide. 87% carbon dioxide, 9% carbon monoxide, and only 4% water by mass. For comparison, most solar system comets are water-rich. Halley's Comet is about 80% water ice. So is Comet Hale-Bopp. This is the opposite. 3I Atlas is carbon-rich with just enough water to create what we're seeing. That composition tells us about where it formed, about the conditions in its home system. The high carbon content suggests a colder, carbon-rich environment, possibly around a different type of star. But it also raises questions about the water vapor we're detecting. If water is only 4% of the mass, why is it so prominent in observations? Why is it the first thing we noticed? The Keck Observatory's Cosmic Web Imager added another piece to this puzzle in late August. They captured detailed spectroscopic images showing not just the water and carbon compounds, but something unexpected: strong nickel emission in the coma surrounding the nucleus. Nickel in comets isn't unusual by itself. Many comets show trace amounts of metallic elements. What's unusual is the ratio and the behavior. The Keck data showed intense nickel lines without corresponding iron signatures. In every natural astronomical object we've studied, nickel and iron appear together. They're formed together in stellar nucleosynthesis. They condense together in protoplanetary disks. They're chemically bonded in meteorites. Except here. Here we have nickel without iron. The research team proposed an explanation: natural formation of nickel tetracarbonyl through a carbonyl chemical process near the nucleus. This is the same process used industrially to refine pure nickel. It involves nickel reacting with carbon monoxide under specific conditions to form NiCO4, a compound that concentrates nickel while leaving iron behind. It's a clever explanation, and it might be correct. But here's what makes people uncomfortable. This process requires very specific conditions: the right temperature range, the right pressure, the right chemical environment. In industrial settings, we engineer these conditions carefully. Could nature replicate this accidentally? On an object traveling through the vacuum of space? The researchers say yes, that the unique chemistry near the comet's nucleus could create these conditions naturally. And maybe they're right. But it's worth noting that we've never seen this happen before, not in any of the thousands of comets we've observed, not in any meteorite analysis, not in any laboratory simulation of early solar system chemistry. Just here, just now, on an object that came from somewhere else. The cyanide signature adds another layer. Cyanide, or CN, is common in comets, formed from carbon and nitrogen. But the distribution pattern around 3I Atlas is asymmetric in a peculiar way. The Keck images show the CN extending in both the solar and anti-solar directions, creating what's called an anti-tail. Anti-tails happen when dust particles lag behind a comet's motion, creating an apparent tail pointing toward the sun. But here's the strange part. The white light images, which should show this dust clearly because dust scatters sunlight, show no evidence of a conventional tail. No dust tail. Just the gas emissions. Just the nickel and the cyanide, glowing in the darkness, arranged in a pattern that doesn't match our models. Some researchers suggested the anti-tail appearance might be an artifact, a smearing of the image from the comet's rapid motion during long exposure photography. But multiple observations from different instruments show the same pattern. It's real. We just don't fully understand what's causing it. Now let's talk about the trajectory. Because this is where things start to feel less like cosmic coincidence and more like precision engineering. When Abraham Loeb's team at Harvard analyzed the orbital path of 3I Atlas, they found something remarkable. The orbit lies almost perfectly in the plane of the ecliptic. That's the flat disk where all the planets orbit the sun. The inclination is just 5 degrees off this plane. 5 degrees. Out of 360 possible degrees in three-dimensional space. They calculated the probability of this happening by random chance. 0.02%. That's 0.02%. And it gets better. Not only is it in the ecliptic plane, but it's moving retrograde, backwards, against the direction of planetary motion, like a car driving the wrong way on a highway. This combination, being in the plane but moving backwards, drops the probability even further. 0.005%. 1 in 20,000. Those are the odds of an interstellar object randomly arriving on this specific trajectory. But here's what really caught their attention. As 3I Atlas moves through the solar system, it will make close approaches to 3 planets: Venus, Mars, and Jupiter. Not just passing vaguely near them, but close enough for gravitational interaction. Close enough for what spacecraft engineers call gravitational assists, or gravity slingshots. When we send probes to the outer solar system, we plan these encounters meticulously. Voyager, Cassini, New Horizons, they all used planetary flybys to gain speed without burning fuel. It's orbital mechanics, using a planet's gravity to alter course and velocity. It's how we explore the solar system efficiently. The trajectory of 3I Atlas provides 3 such opportunities. 3 chances to gain velocity, to adjust course, using the gravity of Venus, Mars, and Jupiter. The Harvard team calculated the odds of this happening randomly. 0.005%. 1 in 20,000. Again. Now, these are separate calculations. The ecliptic plane alignment is one statistical anomaly. The 3 planetary encounters are another. Combined, you're looking at probabilities that make statisticians uncomfortable. Could it be chance? Of course. Unlikely things happen. Somewhere in the galaxy, an object had to win this cosmic lottery. Maybe it's this one, or maybe it's not chance. The team was careful not to make claims. They said, and I quote, "We absolutely do not assert artificial origin as fact, but consider it incorrect to completely exclude such a possibility." Academic language for, we can't ignore this. There's another detail about the trajectory that's worth considering. 3I Atlas approached from the direction of the galactic center, from that dense region packed with bright stars, where spotting a small, dark object is nearly impossible. And its closest approach to the Sun, its perihelion, occurs on October 29th. Right now, as it reaches peak activity, Earth is on the opposite side of its orbit. We're positioned where we can't get a good look at it during its most active phase, almost as if the timing was designed to minimize observation opportunities. The Loeb team noted this too. They suggested that if someone wanted to survey the solar system while avoiding detection, this would be a reasonable approach vector. Come in from the blind spot. Time the perihelion when Earth is elsewhere. Use the planets for course corrections. It's speculative. It's the kind of thing that gets you labeled as fringe in academic circles. But it's also based on hard mathematics and orbital mechanics. The numbers don't lie. The trajectory is statistically anomalous. Then came October 2nd, and everything got more complicated. NASA's Mars Reconnaissance Orbiter has a camera called HiRISE, the High Resolution Imaging Science Experiment. It's designed to photograph the Martian surface in incredible detail, with a resolution down to 30 centimeters per pixel. But it can also point at space. On October 2nd, as 3I Atlas passed within 30 million kilometers of Mars, HiRISE was aimed directly at it. The pixel resolution at that distance would be about 30 kilometers, roughly 3 times better than our best Earth-based telescope images. These weren't casual snapshots. This was a planned observation campaign. Coordinates calculated months in advance. Spacecraft orientation adjusted. Exposure times optimized. NASA wanted to see this object up close. The images were taken. The data was transmitted back to Earth. And then, silence. Normally, high-rise images are released publicly within a few days, sometimes hours. The team at the University of Arizona processes the data and posts it to their public archive. It's standard procedure. Transparency in publicly funded research. But the 3i Atlas images haven't been released. Not yet. It's been over 2 weeks. Now, there could be innocent explanations. Data processing delays, quality issues, review procedures, government shutdown affecting JPL operations. These things happen. But it's unusual, especially for such a high-profile target. Especially when European Space Agency missions like ExoMars and Mars Express have already released their images of the same event. ESA showed their data. NASA hasn't. What did HiRISE see? What's in those images that requires extended review? We don't know. And the silence is creating speculation. Some researchers have expressed frustration publicly. Why the delay? Why aren't we seeing the best images we have of this object? If it's just a comet, what's the issue? No official explanation has been provided. Just waiting. Just silence. Meanwhile, other spacecraft continue their observations. The European Space Agency's JUICE mission, currently en route to Jupiter, photographed 3i Atlas on November 2nd. Those images were released within days. They show the comet, the coma, the unusual emission patterns. Exactly what we expected based on earlier observations. But JUICE was further away. Its resolution wasn't as good as HiRISE. We still don't have those detailed close-up views from Mars orbit. The Juno spacecraft, orbiting Jupiter, will get its chance in March 2026. By then, 3i Atlas will be outbound, moving away from the Sun, potentially less active. HiRISE had the optimal geometry, the closest approach, the best lighting conditions. And we're not seeing what it saw. There's another spacecraft angle to this story that's equally fascinating. The Europa Clipper probe, launched recently toward Jupiter's icy moon, is currently on a trajectory that might intersect with the ion tail of 3i Atlas. Ion tails from comets can stretch for hundreds of millions of kilometers. They're composed of charged particles, atoms and molecules, stripped of electrons by solar radiation. These particles flow away from the Sun, pushed by the solar wind, creating a long invisible stream behind the comet. We can't see ion tails directly in visible light unless they're extremely dense. But spacecraft can detect them, can fly through them, can measure their composition with onboard instruments. Researchers calculated that between October 30th and November 6th, Europa Clipper will be positioned where 3i Atlas's ion tail should be. If the solar wind conditions are right, if the tail extends far enough, the spacecraft could pass directly through it. Europa Clipper has magnetometers. It has plasma detectors. It has particle analyzers designed to study Jupiter's magnetic environment. Those same instruments could sample the tail of an interstellar comet. This would be historic. We've never directly sampled material from an interstellar object. Oumuamua left before we could react. Borisov was observed, but never touched. This could be our first real contact with matter from another star system. The question is, will NASA activate those instruments? Will they take the measurements? The paper proposing this opportunity was published. The calculations are solid. The window is narrow, but achievable. But there's been no public confirmation of whether the observation will happen. No press release. No mission update. Just the possibility, hanging there as the spacecraft flies through space and time runs out. It's not just Europa Clipper. The ESA's Hera spacecraft, heading to study the Didymos binary asteroid system, will also pass through the potential tail region between October 25th and November 1st, right at peak activity. But Hera doesn't have the right instruments for this kind of measurement. It's designed for asteroid observation, for studying the DART impact site, not for detecting tenuous ion streams. ESA confirmed they can't make useful measurements even if they're in the right place. So Europa Clipper is our chance, the only spacecraft in the right place at the right time with the right tools, and we're waiting to see if the opportunity will be taken. Let's talk about size. because this is another piece of the puzzle that doesn't quite fit. Initial estimates put the nucleus of 3I Atlas somewhere between 2 and 6 kilometers in diameter. That's large, really large for an interstellar object. To put it in perspective, Oumuamua was maybe 400 meters long. Comet Borisov was less than a kilometer across. This is 10 times bigger, maybe more. The mass estimates are equally impressive, approximately 30 billion tons. That's 30,000 million kilograms of rock and ice traveling at 58 kilometers per second, carrying kinetic energy that would make a nuclear arsenal look modest. Here's why the size matters. Ejecting an object this massive from another star system is hard, really hard. When planets form, leftover debris gets scattered. Small objects can be kicked out by gravitational interactions with giant planets. This happens in our solar system all the time. Jupiter flings comets into interstellar space regularly, but Jupiter flings small comets, objects measured in hundreds of meters, maybe a kilometer or two. Ejecting something 6 kilometers across requires serious gravitational disruption, a close encounter with a massive planet, a near miss with another star, something violent in the object's history. The probability of such a large object being ejected, and then, by chance, wandering into our solar system is small. Not impossible, but small. And we've now seen 3 interstellar visitors. 2 were small. 1 is enormous. Statistical sampling suggests we should be seeing more small objects than large ones. The ejection mechanisms favor smaller masses. Yet, here we are, with a giant. Unless it wasn't ejected by accident. Unless it left deliberately. That's speculation, obviously, but it's the kind of speculation that emerges when the data doesn't match the models. There's another aspect of 3I Atlas's behavior that's causing quiet discussions among researchers. It has to do with acceleration, or rather, the lack of it. When Oumuamua passed through our solar system in 2017, it did something unexpected. After rounding the sun and heading back to interstellar space, it accelerated. Not much, just a tiny boost, but enough to be measurable and significant. This acceleration couldn't be explained by gravity alone. Something was pushing it. The leading theory suggested outgassing, like a comet. Even though Oumuamua showed no visible coma or tail, the idea was that volatile materials were vaporizing on the sunlit side, creating a tiny rocket effect. It was a controversial explanation. Many scientists found it unsatisfying. The acceleration pattern didn't quite match comet models. The object was too small, too hot, too inactive to be losing material at the necessary rate. But it was the best natural explanation available. Now we have 3I Atlas, which definitely is a comet. It has a coma. It has emissions. It's actively releasing gas, and possibly dust. It should be experiencing non-gravitational acceleration from outgassing. All that material streaming away from the nucleus should be pushing it, changing its trajectory measurably. But it's not. Or at least barely. Detailed orbital analysis published in September showed that 3I Atlas exhibits minimal non-gravitational acceleration, far less than expected for an object releasing 40 kilograms of water per second, plus all the carbon dioxide and carbon monoxide. The outgassing is real. We can see it, measure it, analyze its composition, but it's not affecting the trajectory the way it should. This is backwards from Oumuamua. That object accelerated without visible outgassing. This one outgasses without significant acceleration. One explanation is that the emissions are symmetrical, balanced, canceling out. Gas escapes equally in all directions, so the net force is zero. But observations show asymmetric patterns, that anti-tail, directional features in the coma. It's not symmetrical. Another possibility is that the mass is so large that the outgassing force is negligible. 40 kilograms per second sounds like a lot, but compared to 30 billion tons, it's nothing. The rocket effect is too weak to matter. The math supports this. sort of. But it also means that the water production we're seeing, which is already anomalous for the distance, is even more remarkable. Because it's not affecting the object's motion in detectable ways. It's almost as if the emissions are separate from the propulsion, as if the water vapor is a byproduct, not a driving force. I'm not saying that's what's happening. I'm saying the data allows for that interpretation, and that interpretation raises uncomfortable questions. Let's compare this to what we know about the other interstellar visitors. Oumuamua arrived first, tumbling rapidly, reflecting light in a way that suggested an elongated shape, maybe 10 times longer than it was wide, cigar-shaped or possibly disc-shaped, depending on which model you prefer. It was dark, reddish, reflective like organic rich material or bare rock. No coma, no tail, no obvious comet activity, and yet it accelerated. Abraham Loeb famously suggested it might be a light sail, a thin artificial structure pushed by solar radiation. The idea was met with skepticism, sometimes hostility, from the astronomical community. The consensus settled on the outgassing explanation, despite its problems. Then came Borisov, and everyone relaxed. Finally, a normal interstellar comet. It looked like comets from our solar system. It behaved like them. Water ice, carbon monoxide, a nice bright coma, a proper dust tail. It followed the rules. Borisov proved that interstellar comets exist and that they can be ordinary. Just frozen debris from another star's planetary system, wandering the galaxy, occasionally passing through. And now, 3I Atlas, which has some characteristics of a normal comet, the coma, and emissions, but also has all these anomalies. The water at 3AU, the nickel without iron, the trajectory statistics, the size, the missing acceleration. It's like something in between. Not clearly artificial like Oumuamua might be, not clearly natural like Borisov seems to be. Ambiguous. Designed to be ambiguous, if you're inclined toward that interpretation. Loeb's team created a classification system for anomalous objects, a scale from 1 to 10, rating how unusual something is compared to natural expectations. They gave 3I Atlas a score of 4, not definitively artificial, but significantly anomalous. Worth serious investigation with an open mind about all possibilities. 4 out of 10. That's their assessment based on the accumulated data. The trajectory, the composition, the emissions, the size, the timing, all of it factored into a numerical rating that says, this deserves attention. Other researchers have been more cautious. They emphasize natural explanations. The carbonyl process for nickel, internal heat for the water, coincidence for the trajectory, large size as rare but possible. They're not wrong. Every individual anomaly can be explained, individually, with enough assumptions. But together, all of them, in the same object, that's where the probability calculations start to sting. And there's one more detail that I haven't mentioned yet, something that emerged from the spectroscopic analysis that adds another layer of strangeness. The cyanide distribution around 3I Atlas isn't just asymmetric. It extends in both directions along the comet's path, creating what looks like a forward extension, as well as the anti-tail. Forward gas emissions don't make physical sense for a comet. Gas and dust are pushed away from the sun by radiation pressure and solar wind. They trail behind or stream to the side. They don't precede the object in its direction of travel, unless there's another force involved. Unless the object is releasing material forward, deliberately. The research papers are careful with language here. They talk about projection effects, viewing geometry, possible dust grain behavior under unusual electromagnetic conditions. They provide natural mechanisms that could, theoretically, create this appearance. But they also note that it's unprecedented. We've never seen this pattern before, not in any comet observation in the history of astronomy. So, where did this thing come from? Can we trace it back to its home star? The trajectory tells us the general direction. From the galactic center region, that dense cluster of stars in Sagittarius. But that's like saying someone came from somewhere in Asia. The galactic center region contains billions of stars. Researchers have tried to backtrack the orbit, to calculate where 3i Atlas was thousands or millions of years ago. The problem is that uncertainties accumulate. Small errors in measuring current position and velocity become huge errors when you extrapolate backward across interstellar distances. The best we can say is that it came from that general direction, from a star system somewhere in the inner galaxy. Maybe a close encounter with another star perturbed its orbit, sent it on this path. Maybe it's been wandering for millions of years, slowly drifting through the void until gravity caught it. Or maybe it's newer than that. Maybe it left its home system recently, deliberately aimed at our solar system with specific arrival timing. That's speculation without evidence. But it's the kind of speculation that fits the trajectory statistics. What we can determine is something about the environment where it formed. The chemical composition gives us clues about its birthplace. That high carbon content, the CO and CO2 dominance, suggests formation in a colder region of a protoplanetary disk, further from the parent star than where Earth formed. Carbon compounds condense at lower temperatures than silicates. This thing likely formed beyond the snowline of its system, wherever that was. The presence of water, even in small percentages, tells us the star wasn't too hot, wasn't too active. Water ice requires specific conditions to survive. Too much ultraviolet radiation, too much stellar wind, and it gets stripped away before it can accumulate. So we're looking at an object from a planetary system with a relatively calm star, with a cold outer region, where ices could condense. Not unlike our own solar system in basic architecture. But then there's the nickel signature. Natural nickel abundance in stellar systems follows predictable patterns based on stellar nucleosynthesis. The star's mass, age, and metallicity determine how much nickel ends up in its planetary system. The concentration and purity of nickel we're seeing in 3i Atlas's coma is unusual. Not impossible, but unusual. It suggests either a very specific formation environment with anomalous nickel enrichment or post-formation processing. That carbonyl pathway the researchers proposed could explain it. Nickel tetracarbonyl, forming naturally in the comet's subsurface, concentrating the metal, creating this pure nickel signature we're detecting. It's chemically plausible, but it requires such specific conditions. The right temperature, around negative 170 degrees Celsius. The right pressure, the right chemical mix. Carbon monoxide needs to be present in high concentrations, which it is, but the process also needs time, stability, specific catalytic surfaces. In industrial settings, we use prepared catalysts, controlled environments. Could this happen naturally inside a comet? The researchers say yes, and they may be right. But consider this. We've studied comets intensively for decades. We've sent spacecraft to them. Giotto visited Halley. Stardust collected samples from Wild 2. Rosetta orbited and landed on Churyumov-Gerasimenko for years, analyzing its composition in exhaustive detail. Never once have we seen this nickel without iron signature. Never once has the carbonyl process been detected or even suspected in any solar system comet. Only here. Only in an object from somewhere else. Maybe solar system comets don't have the right conditions. Maybe 3i Atlas formed in an environment just different enough to allow this chemistry. Maybe we're learning that planetary systems are more diverse than we thought. Or maybe this particular object is special for reasons beyond its chemical composition. There's an interesting parallel to consider. In 2014, a small meteoroid entered Earth's atmosphere over Papua New Guinea and burned up over the Pacific Ocean. The military sensors detected it. The trajectory data showed it was moving too fast to be from the solar system. Hyperbolic orbit. Interstellar origin. This was before Oumuamua, before we had confirmed that interstellar objects could visit our system. The data sat in classified databases for years until researchers obtained permission to analyze it. The object, designated CNAS 2014-108, was small, maybe half a meter across. It burned up completely at high altitude, fragmenting into tiny pieces that scattered across the ocean. But some fragments might have survived, might have reached the seafloor. Abraham Loeb organized an expedition in 2023 to search for them. They used specialized equipment, magnetic sleds dragged across the ocean bottom, collecting anything metallic, and they found spherules, tiny molten droplets frozen in mid-flight, with unusual chemical compositions. The composition didn't match any known solar system meteorite class. It showed enrichment in certain elements, depletion in others. The team published papers suggesting this was material from interstellar space, possibly even from a technological origin. The claims were controversial. Other researchers questioned the methodology, the interpretation, the possibility of terrestrial contamination. The debate continues. But let's assume, for a moment, that those spherules are genuine interstellar material. That would mean we've touched two interstellar objects. One tiny meteoroid that we didn't even know to look for until after it was gone, and potentially 3I Atlas, if Europa Clipper flies through its tail. Two contacts. Two opportunities to analyze matter from beyond our solar system, both involving unusual chemistry, both raising more questions than answers. The Cneos meteoroid was fast, incredibly fast. Its impact velocity suggested it wasn't just passively drifting through space. It was moving with purpose, with energy that required explanation. The proposed explanations included close stellar encounters, supernova shockwaves, ejection from a stellar system through multiple gravitational interactions, all possible, all requiring specific, unlikely scenarios. Or, as Loeb suggested, propulsion, artificial acceleration, an object designed to move fast, to travel interstellar distances in reasonable timeframes. That suggestion was dismissed by most of the scientific community. Too speculative, too extraordinary without extraordinary evidence. But here's the thing. If you wanted to explore the galaxy, if you had the technology to send probes to other star systems, how would you do it? You'd need small, durable objects, autonomous or semi-autonomous, capable of surviving interstellar space for potentially thousands of years, able to navigate, to make course corrections, to gather data. You probably wouldn't make them look like spacecraft. Too much surface area, too much drag from interstellar medium. You'd make them dense, compact, shaped to minimize erosion from gas and dust during the journey. Like rocks, like comets, like natural objects that wouldn't attract attention. And if you wanted to study a star system, you'd approach from an angle that maximizes observation time while minimizing detection risk. You'd use the planets for gravitational assists to survey multiple worlds efficiently. You might release smaller probes, sensors, communication relays, things that look like outgassing, like natural material shedding from a comet. You might even disguise propulsion as natural processes. Make it look like comet emissions. Make trajectory adjustments that mimic gravitational perturbations. I'm not saying that's what's happening. I'm saying that if it were happening, this is what it would look like. The scientific method requires us to consider all hypotheses consistent with the data. Natural explanations first, because they're more likely. But when natural explanations require increasingly specific assumptions, increasingly unlikely coincidences, we have to expand our thinking. Loeb's scale rating of 4 out of 10 for 3I Atlas is based on this logic. It's not proof of anything artificial. It's a measure of anomaly, of deviation from expectation. It says, this object warrants serious investigation with all possibilities on the table. Other researchers are more conservative. They see the same data and conclude, unusual but natural. Comets are diverse. Interstellar space is vast. We've only observed 3 interstellar objects, Our sample size is too small to determine what's normal versus what's anomalous. Both perspectives are valid. Both are based on the same observations, interpreted through different frameworks. But here's what makes this moment important. We're finally in a position to get better data. We have spacecraft in the right place. We have telescopes focused on this object. We have the technology to answer some of these questions definitively. The high-rise images, when they're released, will show us details we've never seen before. Surface features, rotation patterns, structural characteristics. We'll be able to see if the nucleus is uniform or composite, smooth or rough, symmetrical or irregular. If Europa Clipper samples the ion tail, we'll get isotopic ratios. Deuterium to hydrogen, carbon-13 to carbon-12, nitrogen-15 to nitrogen-14. These ratios are fingerprints of formation conditions, of stellar environment, of chemical history. We'll be able to compare 3I Atlas directly to solar system comets, to Borisov, to meteorites from the early solar system. We'll see if it's truly different or if our expectations were just wrong. The Juno observations in March will add another data point. Different viewing angle, different instruments, different phase of activity. If 3I Atlas is still outgassing then, we'll learn about the longevity of its emissions. If it's gone quiet, we'll learn about what triggered the activity in the first place. Every piece of data constrains the possibilities. Every observation narrows the range of viable explanations. And that's why this object matters so much. Not because it's definitely artificial, but because it's definitely anomalous. And anomalies are how we learn. Think about the history of astronomy. Every major breakthrough started with an anomaly, something that didn't fit the models. Mercury's orbit didn't match Newtonian predictions. That anomaly led to general relativity. Stars and galaxies moved too fast for visible matter. That anomaly led to dark matter. The universe's expansion was accelerating. That anomaly led to dark energy. Anomalies are invitations. Invitations to look closer, to question assumptions, to expand our understanding. 3I Atlas is an anomaly. Multiple anomalies, actually, layered together in one object. And whether the ultimate explanation is natural or artificial, we will learn something profound from studying it. If it's natural, we'll discover new physics of cometary behavior. We'll learn that objects from other stellar systems can have chemistries and dynamics we never anticipated. We'll expand our catalog of what's possible in planetary formation. If it's not natural, well, that changes everything. Consider the implications of that second possibility. Not asserting it, just considering it. If even one interstellar object is artificial, it means we're not alone. It means technological civilization has arisen somewhere else in the galaxy. It means intelligence is not unique to Earth. More than that, it means they're exploring. They're sending objects across interstellar distances. They have the technology, the resources, the motivation to study other star systems. And if they're doing it, they're probably not alone. One civilization with interstellar capability suggests others. Many others, perhaps, across the galaxy's billion-year history. The galaxy could be filled with these objects. Small, durable, autonomous probes, traveling between stars, observing, collecting data, maybe communicating, sending information home or to each other. We've only confirmed 3 interstellar objects, but our detection capabilities are limited. We find these things by accident, by lucky timing, by them happening to pass close enough and bright enough to spot. Researchers have estimated that dozens of interstellar objects pass through the inner solar system every year. Hundreds if you count smaller ones. Thousands if you include objects we could never detect with current technology. Most pass through unnoticed. They don't come close to the sun, so they don't brighten. They don't develop tails. They're dark, small, fast, and we simply miss them. Of those we do detect, how many might be artificial? How many could we recognize as artificial with our current observational methods? If someone showed you a dark, tumbling rock moving through space, could you tell if it was natural or designed? Unless it was obviously shaped, obviously structured, probably not. Oumuamua could have been either. We'll never know. It's gone, receding into interstellar space, and we'll never see it again. Borisov seemed natural, but we only observed it for a few months. We saw a comet behaving like a comet. That's what we expected to see. 3I Atlas is still here, still observable, still producing data. And the more we look, the stranger it gets. That strangeness is valuable, regardless of its source, because it forces us to confront our assumptions. We assume comets behave certain ways. We assume chemistry follows predictable patterns. We assume trajectories are random. We assume nature is the default explanation. These are good assumptions, usually. They've served science well, but assumptions can also blind us. If we're too committed to natural explanations, we might miss evidence of artificial ones. If we're too quick to dismiss anomalies as measurement errors or rare flukes, we might overlook genuine discoveries. The scientific community struggles with this balance. On one hand, extraordinary claims require extraordinary evidence. We can't call everything aliens just because it's weird. That way lies pseudoscience and credulous thinking. On the other hand, we can't be so conservative that we refuse to consider possibilities that challenge our worldview. That way lies stagnation and missed opportunities. Loeb has been criticized for his willingness to suggest artificial origins for Oumuamua and now 3I Atlas. Some colleagues see it as attention-seeking, as lowering scientific standards, as giving credibility to UFO enthusiasts. But Loeb argues that the bias goes the other way, that the scientific community is too reluctant to consider extraterrestrial technology as a hypothesis, that we apply different standards to SETI, listening for radio signals, than we do to looking for physical artifacts. We spend millions searching for signals from alien civilizations. We build radio telescopes. We scan the skies. We assume that if intelligence exists out there, it might communicate. But when an unusual object passes through our solar system, an object with characteristics that don't match natural predictions, we reflexively dismiss artificial explanations. We bend over backward to find natural mechanisms, no matter how contrived. Why? What makes radio signals a respectable search target, but physical probes unscientific? Both are legitimate hypotheses. Both are worth investigating. Both deserve serious consideration when evidence warrants it. The evidence for 3I Atlas being artificial is not conclusive. It's circumstantial, statistical, based on probabilities and anomalies. But it exists. It's there in the data, and the appropriate response is not dismissal. It's investigation. Rigorous, skeptical, thorough investigation. That's what makes this moment exciting. We have the opportunity to investigate. We have spacecraft, telescopes, instruments designed to gather exactly the kind of data we need. The question is whether we'll use them. Whether institutions like NASA will prioritize these observations. Whether the scientific community will engage with the results openly and honestly. The high-rise silence is frustrating because it suggests hesitation, as if the data might be too controversial to release quickly, as if there's internal debate about interpretation, about implications, about how to frame the findings. Maybe that's unfair. Maybe the delay is purely technical. But perception matters, and the perception is that something unusual is happening. Meanwhile, time is running out. 3I Atlas is moving fast. It passed perihelion on October 29th. By December, it will be beyond Mars' orbit, receding, cooling, potentially going dormant. The window for close observation is narrow. Every day matters. Every data point matters. If we miss this opportunity, If we fail to make the measurements we can make right now, we might regret it for generations. Because we don't know when the next interstellar visitor will arrive. Could be next year, could be decades. And the next one might not be as anomalous, might not provide the same invitation to investigate. This is our moment, right now. October 2025. With 3i Atlas in our solar system, active, observable, weird enough to warrant serious attention. What we learn in the next few months could reshape our understanding of the universe and our place in it. Or it might just teach us that comets are more diverse than we thought. That interstellar space produces objects with unusual chemistry. That our models need refinement. Either way, we learn. Either way, we advance. But the stakes are different. One outcome is incremental progress in planetary science. The other is confirmation that we're not alone, that intelligence exists elsewhere, that the galaxy is populated and explored. Those are not equivalent outcomes, and that's why the reluctance to consider the second possibility is so strange. What are we afraid of? What's the worst that happens if we investigate seriously and find nothing artificial? We've wasted some telescope time. We've redirected some spacecraft instruments. We've published papers that turned out to be wrong. That's normal science. That's how research works. But what if we don't investigate and we miss it? What if 3i Atlas is exactly what the anomalies suggest, and we were too cautious, too conservative, too committed to conventional thinking to recognize it? That's the greater failure. Not looking when we had the chance. Not asking the questions when the evidence was right in front of us. History is full of missed opportunities, of data that was misinterpreted or ignored because it didn't fit expectations. Pulsars were almost dismissed as instrumental artifacts. The cosmic microwave background was initially thought to be pigeon droppings on the antenna. Exoplanets were considered impossible until we found thousands of them. Science progresses by challenging assumptions, by investigating anomalies, by being willing to be wrong in pursuit of being right. 3i Atlas gives us that opportunity, and the clock is ticking. So what happens next? What should we be doing right now to maximize what we can learn from this encounter? First, the high-rise images need to be released. Whatever they show, the scientific community and the public deserve to see them. These were taken with taxpayer-funded instruments on a taxpayer-funded mission. Transparency is not optional. If there are concerns about interpretation, about public reaction, those can be addressed through proper contextualization. But withholding data serves no one. It only fuels speculation and erodes trust. Second, NASA needs to clarify whether Europa Clipper will attempt to sample the ion tail. The window is closing. If the decision is no, we deserve to know why. If it's yes, we deserve to know what instruments will be activated and when results will be available. This isn't just scientific curiosity. This is potentially the first direct sampling of interstellar material in human history. The first time we touch something from beyond our solar system. That matters. Third, the broader astronomical community should be coordinating observations. Every telescope, every instrument that can contribute should be focused on this object while we still have the chance. Ground-based observatories, space telescopes, radio dishes, infrared sensors. We should be collecting every wavelength, every spectrum, every data point possible. Because once it's gone, it's gone. 3i Atlas is moving at nearly 60 kilometers per second. By spring 2026, it will be past Jupiter's orbit. By 2027, it will be fading from view entirely. Within a decade, it will be back in interstellar space, unreachable. This is our window, our only window. And beyond the immediate observations, we need to be thinking about the future, about how we handle the next interstellar visitor. Because there will be another one. Maybe soon. Maybe not for years. But they're out there, passing through our solar system regularly, and we're only catching the ones that happen to come close and bright. We need better detection systems, wider field surveys, automated alert systems that can spot unusual trajectories in real time. The Vera Rubin Observatory, when it comes fully online, will help. It's designed to scan the entire visible sky every few nights, looking for anything that moves or changes. Asteroids, comets, supernovae, and yes, interstellar objects. With Rubin, we should catch these visitors earlier, when they're still inbound, when we have time to react, time to plan observations, time to potentially send a spacecraft. Several proposals exist for rapid response interstellar object missions. Small probes kept ready for launch, able to reach an incoming visitor within months if we detect it early enough. The technology exists. The challenge is funding, prioritization, political will. Do we value this enough to invest in it? Do we consider the search for extraterrestrial artifacts important enough to dedicate resources? The answer to that question reveals something about us as a civilization, about whether we're truly committed to exploration, to discovery, to understanding our place in the cosmos, or whether we're content to watch from a distance, to speculate without investigating, to wonder without seeking answers. 3i Atlas is testing that commitment. It's showing us what's possible if we pay attention, if we use the tools we have, if we ask the hard questions. But it's also showing us what we're missing. The delayed images, the uncertain spacecraft observations, the lack of coordination, the institutional hesitation. We can do better. We must do better. Because here's the thing. If 3i Atlas is natural, we're learning about cometary diversity, about planetary system formation around other stars, about the chemical evolution of the galaxy. That's valuable. That advances our understanding. But if it's not natural, if there's even a small chance it's something more, then every day we delay, every observation we skip, every question we don't ask is a missed opportunity of historic proportions. We're not talking about incremental scientific progress. We're talking about the discovery that would define our generation, our century, our entire civilization. The first confirmed evidence of extraterrestrial technology. The proof that we're not alone. The knowledge that intelligence exists elsewhere and is capable of interstellar exploration. That's what's potentially at stake. And we're treating it like routine comet science. Maybe that's appropriate. Maybe the natural explanation is correct, and all these anomalies are just coincidences, rare but possible configurations of ice and rock. But maybe it's not. Maybe we're living through a moment that historians will look back on as pivotal. The moment when humanity had the chance to recognize visitors from another world and either rose to the challenge or failed to see what was right in front of us. The choice is ours. The data is coming in. The spacecraft are in position. The telescopes are watching. What we do with this information, how we interpret it, whether we pursue it aggressively or cautiously, openly or secretly, will say as much about us as it does about 3i Atlas. There's a broader context to consider here. We're living in an era of unprecedented astronomical discovery. Thousands of exoplanets found, gravitational waves detected, black holes imaged, the cosmic microwave background mapped. We've learned more about the universe in the last 2 decades than in all of human history before that. Our understanding has exploded. And part of that explosion is the realization that the universe is far more dynamic, far more diverse, far more populated than we imagined. Planets are everywhere. Rocky worlds, gas giants, ocean planets, lava worlds, rogue planets drifting between stars. The galaxy is full of them. Many of these planets exist in habitable zones, regions where liquid water could exist, where chemistry could become biology, where life might arise. We don't know how common life is. We've only found it on one world. But the ingredients are everywhere. The conditions are common. The chemistry is universal. Intelligence is a different question. Life might be abundant, but technological civilization might be rare. Or maybe not. We don't have enough data. What we do have is mathematics, statistics. The Drake equation, for all its uncertainties, suggests we shouldn't be alone. The sheer number of stars, planets, opportunities for life to emerge and evolve suggests that somewhere, sometime, it happened. And if it happened elsewhere, why wouldn't they explore? Why wouldn't they send probes, build telescopes, search for others? We're doing it. We've sent Voyager to interstellar space. We're planning missions to Alpha Centauri with laser-pushed light sails. We're building instruments to detect biosignatures on exoplanets. We're exploring because that's what intelligence does. It wonders. It questions. It seeks. Why would we be unique in this? Why would curiosity be exclusive to Earth? It wouldn't. And if others are exploring, if they've been exploring for millions of years across billions of star systems, then statistically, some of their probes should pass through our neighborhood. 3 confirmed in 8 years. That's what we've found so far, with limited detection capabilities, and mostly by luck. How many have we missed? How many are out there right now, moving through the outer solar system, too far or too dark to spot? We might be swimming in a sea of interstellar visitors and only noticing the ones that practically hit us in the face. 3i Atlas didn't hit us, but it came close enough, bright enough, active enough, strange enough. It got our attention. The question is, what we do with that attention. Do we investigate thoroughly, rigorously, with all possibilities on the table? Or do we observe casually, explain conventionally, and move on? The answer will determine not just what we learn about this object, but what we're prepared to learn about the universe. So why does 3i Atlas matter? Let me bring this full circle. It matters because it's here, right now, passing through our solar system at a moment when we have the technology to study it properly. That timing is extraordinary in itself. 50 years ago, we would have missed it entirely. 100 years ago, we wouldn't have known what we were looking at. But now, in 2025, we have space telescopes, planetary orbiters, interplanetary probes, spectroscopic instruments capable of analyzing composition from millions of kilometers away. We're catching 3i Atlas at exactly the right moment in human technological development. That's either remarkable timing or remarkable luck, or perhaps neither. It matters because every anomaly we've discussed, every statistical improbability, every unexplained behavior forces us to expand our thinking about what's possible, about what exists out there in the galaxy beyond our small corner of space. Whether 3i Atlas is a comet with unusual properties or something else entirely, it's teaching us that the universe is stranger, more diverse, more surprising than our models predict. And that's valuable. That's how science advances. It matters because of what it represents for the future. We're at the beginning of the interstellar object detection era. 3 confirmed visitors in 8 years means there will be more. Many more. And each one will teach us something about the galaxy, about stellar systems, about the materials and objects traveling between the stars. But it also matters because of what it might be. Not what it definitely is, but what it could be. If there's even a 5% chance that 3i Atlas is artificial, that it's a probe from another civilization exploring our solar system the way we're planning to explore theirs, then that 5% chance changes everything. It means we're being watched, studied, cataloged. Our solar system, our planet, our civilization might be entries in someone else's database. Data points in an alien survey of galactic stellar systems. That's not a comfortable thought for everyone. It challenges our sense of uniqueness, our position as potentially the only intelligence in the cosmos. But it's also profoundly hopeful. Because if they exist, if they're exploring, if they've achieved interstellar capability, then it's possible. It can be done. Intelligence can survive long enough, can advance far enough to reach beyond its home star. And if they can do it, maybe we can too. 3i Atlas might be showing us our future, not just through what it is, but through what it represents. The possibility that intelligence can persist, can explore, can send pieces of itself across the vast distances between stars. We're already trying. Voyager 1 and 2 are in interstellar space now, carrying golden records with sounds and images from Earth. Pioneer 10 and 11 preceded them. New Horizons is heading out after its Pluto flyby. These are our first interstellar emissaries. Primitive, simple, slow. They'll take thousands of years to reach even the nearest stars. But they're out there. We sent them. But I know we're being given the chance to find out. 3i Atlas is here. Now. Moving through our solar system. Visible. Observable. Analyzable. This is the moment. This is the opportunity. The question is, what will we do with it?